Hello, I'm Lily Hyam.
And I'm Gordon Johnston. Welcome to the Last Question podcast, a production of DataFest, the ongoing series of data and artificial intelligence innovation events run by the Data Lab, Scotland's innovation centre for data and AI, hosted by the University of Edinburgh.
This is an incredibly exciting episode of The Last Question for us. Today we are joined by Dr. Giovanna Giardino, an astronomer at the European Space Agency currently working on the James Webb Space Telescope project. Dr. Giardino is an instrument scientist with a particular focus on the formation of galaxies and preparation of spectroscopic observations of the atmospheres of extrasolar planets.
For anyone who may have missed it, or if you've been living under a rock for the last couple of months, the James Webb Space Telescope is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It's the world's most powerful space telescope, made up of 18 gold-plated hexagonal mirrors that give it unparalleled vision deep into the cosmos. It's currently around 1.5 million kilometres from Earth in Lagrange point 2, with a Lagrange point being an area of equilibrium for a small object between two much larger objects. So in other words, the telescope stays in place because it's in a sweet spot between the Earth and the Sun, which allows it to stay in a relatively fixed position in relation to the Earth.
The Webb will be able to study galaxies 13.5 billion light-years away, which is only a few hundred years after the dawn of time. It produces its stunning images using infrared technology to capture light from some of the earliest and most distant luminous objects we've ever seen. So Gordon, do you know how to use a telescope?
No, I don't.
You should look into it. There's no laughter, it's just like silence.
The 18 hexagons that make up the telescope's mirror reminds me of the Library of Babel in the short story of the same name. In the story, there's a library that's made up of an infinite number of interconnected hexagons, each one containing volumes of 410-page books, which contain every possible combination of a set of 25 standard characters. So in theory, the library contains all the possible knowledge, past, present, and future in the entire universe, but it's utterly impossible to parse it out without some kind of guide as to where the correct useful knowledge lies. In the story, there's this mystical crimson hexagon, which is a room that has almost like a glossary of where you can find everything.
It'd be really useful to have that glossary because, as we've heard recently, the amount of data that we're receiving from the James Webb Space Telescope is just so much. It's going to take years and years to be able to process all of it. So people are going to have to be patient with getting discoveries from this massive amount of data. We have all this information at our fingertips, but luckily we do have people all over the world who act as a key to unlocking and understanding this information, like the librarians of Babel. And one such librarian of Babel is Dr. Giovanna Giardino. Thank you so much for joining us, Dr. Giardino.
The James Webb Space Telescope has captured the public's imagination in ways we haven't seen in decades. We had the public unveiling of the first images by Joe Biden, the huge displays in Times Square in New York, and the endless news coverage all around the world. Kind of harkened back to the space race in the 60s, where the possibilities of space seemed limitless, and the advancements in space technology and the achievements through those, they were proper international news and cause for international celebration. So since the telescope started sending data back to us, what's been the most exciting thing that you've learned?
I think, to be honest, I found that all the images that were first released are very, very interesting and inspiring because they cover such a wide range of the studies that we can make with this very powerful telescope. So it's very difficult to pick one favorite. But okay, in a way, my favorite are from the very far and the close by. So in the terms of very far, I really found really beautiful and shows really the potential of this machine was what we call the deep field. So the image of the cluster of galaxies with the beautiful gravitational lensing. I think there's so much in the image that we can talk for hours. So, and then we can talk maybe later because there's so much, like I said. And then if you huge jump. So from the very far away galaxies, we are talking 13 billion light years, or really, the edge of the universe to a certain degree, to our galaxy, the neighborhood of our sun. Then we have data from exoplanets. So planets that are orbiting our other stars than our sun. So not planets in our solar system, but around our other stars. And that I found fascinating. So these are other worlds that are around us.
Speaking of exoplanets, it was just yesterday on the 1st of September that the first image of an exoplanet was released by the James Webb, the snappily named HIP 65426b, which is maybe not one of the great planet names, but so it's a gas giant around 5 to 10 times the mass of Jupiter, about 385 light years from Earth, in the Centaurus constellation. So one of your areas of research is the preparation of spectroscopic observations of the atmospheres of exoplanets, such as HIP 65426b.
We need a nickname.
I know, it needs a better name. It needs a way better name. So just for anyone unfamiliar with the term out there, spectroscopy is the study of the absorption and emission of light and other radiation by matter. Could you tell us a bit about how this process works and what we can learn from this kind of information?
Yes. So that's a very interesting technique. So spectroscopy, as you know, it involves dispersing the light. So just like a prism, when you shine lines through a prism, the prism disperses light. You see the colors of the visible light, which are the components of our light. And if you have something better than a prism that can disperse the light even more, then you start to see what we call lines, the signatures of elements. So, for instance, you can understand what are the elements on the sun. If you do spectroscopy of the sun, what is how much oxygen there is, how much hydrogen, helium, and so forth. So for the exoplanets, so we can apply this technique to the observation of exoplanets in a very special way. Some of the exoplanets are aligned in such way that they pass in front of their star to our line of sight. And when the planets pass in front of the star, part of the lights of the stars is absorbed by the atmosphere of the planets. And the absorption depends on the elements that the atmosphere of these planets contain and their physical condition, whether, again, what's the temperature that we're talking about, the pressure. So by looking at this data, this spectroscopy data, during the transit of the planet in front of the star, we can gain information about the composition of the atmosphere of the planet. And that's a very powerful technique because it allows us to learn about what's going on in this alien world.
When you are looking at the data you've got from looking at these exoplanets, is there something, is there a key finding that you're looking for? Some kind of signature of something or a particular element?
It depends on the planet you're looking at. There was a famous release for the observation of CO2 in this gas giant a few weeks ago, and that was important because this planet was known from previous studies, and people were trying to understand more about the physical condition and what was going on. So measuring this feature of the CO2, which was a first, allows them to infer the metallicity, so what type of elements are present and how different it is from a gas giant in our solar system, like Jupiter or Saturn. So this is for gas giant, for instance. Going forward, I'm sure Webb will be pointed also towards observe a transit of exoplanet that looks more like our Earth, so more rocky, more what we call rocky planets, because they have a rock core where we can live on, not floating around in these guys. And then there, of course, the big prize will be looking and see elements that we can relate with the composition of our atmospheres. So oxygen, water, nitrogen, possibly methane, and so on.
One of your papers is on the impact of cosmic rays on the sensitivity of the James Webb Space Telescope and NIRSpec. Is that how you say it? NIRSpec, yes.
Correct. Yes.
How do you mitigate the effect of the noise caused by cosmic rays hitting the telescope and affecting the data negatively?
Yeah, that's a very good question. This is a challenge that Space Telescope and scientific mission all have to face when you are outside, let's say, the magnetic belts that are around our Earth. So here on Earth, we are within this relatively strong magnetic fields of our planet, that shield us to very strong and large fluxes of these high energy particles that fills the space. Partly come from the sun, partly come from high energy event in our galaxy or outside our galaxy. They are extremely high energetic particles. And in fact, it's something that, for instance, astronauts have to deal with, and missions to the moon are particularly challenging in that respect because of this radiation. And our instruments suffer from the disturbance that this particle cause by impacting on our detectors and then giving signals that are what we call spurious. They're not the signal we're looking for. They're just like you say, noise, nuisance. And there are various techniques that we can employ to mitigate, to actually detect, so that we can distinguish the signal from a cosmic ray from a signal from the star. So that's already one way to say, okay, this is not a star. It was just a big shiny pixel because this was hit by a cosmic ray. And on top of that, the detector of the Webb are well designed to cope with this type of disturbance. I don't know whether you want me to go into this more technical detail, but we don't take. I mean, certain camera already works like that, even in consumer electronics. But we don't take one picture like click. And we collapse all the signal. Where we take a picture, we actually keep accumulating the signal. So the camera is staring to galaxies, and we keep looking at the signal, and so we have, if the signal is undisturbed, you have a nice ramp, a nice continuous accumulation of signal. If a cosmic ray hits, you will have a jump in this ramp, because the cosmic ray is an instantaneous event. It's not like photons slowly arriving to your detectors from this galaxy. And so by looking at these jumps in our recorded signal, we can eliminate the imprint of many cosmic rays. Not all of them, but a good fraction, and that allows us to have these beautiful images undisturbed by this problem.
Is there anything else that is also causing noise and errors in the data collection of the telescope apart from cosmic rays?
There is a lot of things that are going on. Okay, detectors always have noise. That's the noise of the electronics, and that's designing good detectors means designing detectors with very low noise. As you can imagine, Webb, a state-of-the-art detector, right? You have a very expensive telescope, so you put the best available detectors, and so in terms of detector noise, they are very, very good performance. So we have a little But we do have it, and again, that can be just simple detector noise can be a challenge if your signal are very low, and we're gonna go with that for it. It's not in the beautiful image you've seen with the release. These are relatively bright objects that were looked at because you want also to test your telescope with things you can see well. But as you dig down, and scientists have already started to do that because they want to look at the very faint galaxy that you've seen, for instance, in the deep field, right? These are the more furthest objects. They're very interesting to understand how galaxy forms. People are very exciting. They're digging in, and there, you have to confront it with the detector signal. So the detector noise, sorry. So that's certainly there, and there are again technique, but that's where statistics come in. So that's where knowledge of statistics allows you to say, okay, I can trust this point. This is really above my noise. This point, it's dodgy. It could be, I'm really fishing into the noise. So normally you will leave it alone and don't trust. That's an example. Of course, we had noises that are not like noises, but like nothing is perfect. So your telescope, although Webb has a fantastic pointing capability, is really, really stable when it's pointed to an object. It's never perfectly stable, so it jitters a bit, and that creates noise because the star is moving a little bit inside your detector, which have slightly different response according to which pixel you're looking at. So that's what we call systematics effect, noise, there are many little things that go and make things complicated. So the life of a scientist is never very simple. Quite opposite.
Yeah, very complicated. What are the things that is causing the slight movements within the telescope? Is it the equipment inside it, the electronics inside?
That's a good question. When you point the telescope, right, you have action and reaction. So as you point it there, then it will have to stabilize. So it fluctuates a bit. There are thermal effects, I think, which are thermal mechanical, right? That that the telescope, it's behind this huge sun shield, right? This kite-like structure that is very striking in the Webb, and this shield shields the telescope from the radiation of the sun, the heat of the sun and the Earth, which are both aligned behind the sun shield, and the telescope is pointed deep into deep space. So we have the error of this telescope, which is about 40 Kelvin, which is minus 230 degrees Celsius. And the hot part, the one towards the sun, which is at about plus 80 degrees. So there's a huge thermal gradient, thermal differences between these two shots. And that, as you can imagine, causes mechanical tension, and small movement will change slightly your thermal distribution and cause movement of your equipment, and that causes vibration. And they're tiny, they're absolutely tiny, but when you're looking for very tiny signal, that also have an impact.
I had no idea the temperature was so extreme. Yeah. How do you dress for that kind of weather?
It is. I think, especially because I come from the instrument side, I really go on how a marvel instrument it is in terms of engineering. The telescope, the spacecraft, the instruments on board. I think. Really, we pushed the capability of our species at the moment of humanity, and in that way, I liked that you made this introduction with the Apollo program. It's still small compared to the Apollo program, and of course, there are no astronauts. We are not going anywhere, let's say, in terms of exploration with humans. But it is really a large program, a program that involves many nations, collaboration across the Atlantic between Europe and America. Canada was also involved, so a lot of expertise from many people, engineers, technicians, scientists, finding the best technology to solve the various problems that came up in designing this amazing machine.
I think one of the most exciting things about all this, or maybe why it's captured the public's imagination, is because it's just unreservedly good news. There's no real caveats. It was just international cooperation where, like you said, we pushed the ability of our species to do something absolutely incredible. And it's really rare that we have anything like that. Usually it's like, oh, there's some good news, but there's a downside. Or here's some good news, but it's like ecologically terrible or something. This is just all good, And when you think the telescope costs, $10 billion, that's nothing in the great scheme of things. We should be spending that every year on this stuff.
I agree with you, but I think it's inspiring, and my personal experience really has been very, very positive in working with this collaboration on the what we call on the working floor. There was always this willingness to work together to solve the problem together with respect for each other, for other ideas. So yeah, in that respect, it's been really a good experience. This is from a personal point of view, but I think the price of this good collaboration, openness, both from NASA and ESA and the Canadian Space Agency to work together, finding what worked, and sometimes leave politics aside, really paid off.
Is it quite difficult to choose what to choose to point the telescope at? Because I imagine there are different scientists have different interests or different things that they think are a priority, and there might be some debate over which they want to have a look at.
Yeah, that's a very good question. So the Webb telescope, it's a general purpose telescope, open time telescope. So scientists from all over the world can propose observations. This happens 2 cycles, so more or less yearly. There's a call for proposal. So the telescope scientific operations managed by the Space Telescope Science Institute in Baltimore. The calls are for proposal. Say to the community, send out your proposal. How would you use the Webb to do what? And that's where lots of scientists scramble and write, and get together and see what can we do, and scramble ideas, and then write a proposal. I say, okay, if you give me 50 hours of Webb, I will use NIRSpec to look at the stars in the Large Magic Lantern Clouds, because, for example, and there are, as you can imagine, there are more proposals that can be executed within 1 year cycle. So let's say the scientists in total ask for more hours than there are in 1 year. Of operation. And so there is a committee. There's a committee of experts and independently selected that look at the proposal and decide which are the most interesting, the most likely to succeed, and provide good data.
Amazing. Again, more international cooperation.
Maybe we should put a proposal together for something.
We absolutely should.
What would you like to look at?
What would I like to look at? I don't know where I'd point it in the sky.
Which object? Which type of object? Without knowing the direction, but which type of object would?
For me, it would have to be like a planet. Galaxies are beautiful and they're these like stunning, massive things, but they feel quite intangible because I don't think an average person can get their head around quite how big a galaxy is. It's unfathomably huge.
I think I would go for galaxies actually, because I think we can learn so much about the early universe, and I kind of want to know about what happened in all that time?
So actually, speaking of this, the James Webb will be looking back about 13.5 billion years, which theoretically is only a few hundred million years away from the birth of the universe. Is it possible to look back even further with a more powerful telescope, or could we ever actually see the beginning of everything? Is there anything to see? What do you think would happen with that?
This is a complicated it's a complicated question. It's a fascinating question. So if you allow me, I'm going to try to go a little bit in some detail. But so how do we say? If you want to be completely correct, the Webb is not the mission which has looked further from us or to the earliest time. We've been mission that we call that have been looking at what we call the cosmic microwave background radiation. There was a famous American mission called COVID, and there was WMAP, again a NASA mission. Recently, 10 years ago, launched Planck, also a mission to observe the cosmic microwave background. And that's what we call the echo of the Big Bang. So the Big Bang was this beginning of the universe, was extremely hot. And at a certain point, the temperature decreased and the photons started propagating freely. So we see what we call the last scattering surface, when the universe, let's say, became transparent to light, was not so dense and hot like a ball of gas and energy, like it's like kind of a star, but the photons start propagating freely, and we can see these photons. They are extremely redshifted, and that's why we look at them in the microwave. So photons that were more or less in the visible are redshifted by a factor of thousands, and we see them in a frequency between 3 to gigahertz to 1,000 of gigahertz, so hundreds of gigahertz. And so this is, if you want, in terms of photons, using photons, because one can also use other techniques like gravitational waves, but in terms of photons, this is in a way the furthest we can go. And these are about 300,000 years after the Big Bang, this last scattering surface. But this is kind of and the big contribution of mission like WMAP and Planck and also COVID at the beginning was to see that in this is not just a uniform ball of energy, but there are slight dishomogeneities in this ball of energy, and this is what causes, these are the gravitational dishomogeneities, which are what we call the seeds of the galaxy, the seeds of the structure, right? If you have a perfect homogeneous ball and it expands, then you don't have anything. Gravity doesn't kind of act, it's all uniform and boring. And with these homogenities, gravity starts to attract matter or dark matter and energy, and that's where we believe galaxies are born, right, from these homogeneities that we see. And but it took time, and with Hubble we saw galaxy at, like you say, 12.5, 13 billion light years ago, and they were there, right? So what happens between the 300,000 years and about a few hundred million years after the Big Bang? A lot happened. These galaxies start to grow, and it's the first stars start to shine. But we have not seen that. We have theoretical model, we have computer simulations that reproduce this stage, but we don't have data from this period. And mission like the Webb have to push our vision to connect these points to try to understand what's happening in these few hundred million light years of time when the galaxies were born and the galaxies where we live. And so these are part of the history of our origin.
Yeah, on the topic of formation of galaxies, can you explain to us what the kind of information we're getting from the Telescope means for our understanding of the universe when we learn about the formation of galaxies?
Right. Yes, thank you, because this is a good question to connect to this long story. Yes. So with the telescope, so we are really aiming at identify the youngest object possible. So this is where we do deep field. So we stare for a long time in the same direction to really reach the weakest object, which are the furthest away, the galaxies which are further away. That's their structure. So how much of a galaxy was there? We know that as we go look back, they are more smaller and more irregular than the beautiful grand structure we see in the universe around us. So how much was there at the time? And then with the spectroscopy, what was going on in terms of star formation? The star was shining. Which elements were already present? Can we see the star that was made only of hydrogen and helium, which would be the first stars, right? Because all other elements are cooked inside the star. So the very first stars should have very little else than hydrogen and helium, if anything. No, nothing.
Just like one last follow-up to that, has our understanding of galaxy formation changed since the James Webb started sending data back?
Well, the scientists are really looking at the data very carefully because of all we have said, right? The noise, all these complicated effects, from the beautiful image you see in the press and released to actually getting scientific data, there is always time. So the data, some of the images that you've seen are being scrutinized as we speak. Some results are already came out, and the people can see a lot of activity, a lot of star formation seems to be happening in galaxies that are at redshift around 7. So very early in time, there is sign of a very active star formation and in low metallicity. So, this is kind of falling into the picture. So as we speak, things are, publications are coming out.
It must be very exciting for some people that have been working only with theories and using computer models to try and work out what's happening, to get this data back and think, is it going to prove my theory correct?
Yes, it's very exciting, and the scientists, so it's not us, we are the instruments people, but the scientists are really telling us that the telescope works better than they even expected, and so this is why there is also so much excitement in the community, because it's clear that there will be very good data coming out. Science, it's an interesting. It's a funny process. You start from an idea that you have, like you say, you have a model and you have math simulation. You think things should go like that. So you're very happy when you find data that confirm or that they're consistent with your hypothesis, that your understanding is advancing. But sometimes your understanding advances even more when you have something you don't understand, or it will take time. It will take time. Clear example is what we call dark energy and dark matter, which are a way to say we don't know much about this entity, right? But to understand about that, it means that we will make big progress. So it's an interesting process in this respect.
You can hear more about Giovanna's incredibly fascinating and exciting work when she comes to join us at Data Summit on the 3rd and 4th of November in Edinburgh at the EICC, and we absolutely cannot wait to have her join us. And with that said, I think it might be time for some wild speculation.
Yes, this is the part of the show where we ask our guests to go beyond the scope of their research or expertise and engage in some wild speculation about their field. Giovanna, in your wildest dreams, what would you like the James Webb Space Telescope to discover?
I think the signature, two things, but certainly it would be fun, how to say, Kepler moment, a revolutionary moment. If we could see the signature of life in the atmosphere of Earth-like planet or rocky planets, and by signature of life I mean the traces of the gases that we think is associated with life. I think that would be it won't be easy. I'm not sure it can happen. No, it's speculation. It's speculation. But it would be and if Webb won't do it, we will need to build a bigger telescope, more powerful, maybe specific for this type of investigation. Yeah.
I think everyone's waiting on that. Anytime there's any advance in space or anytime we find something interesting out there, the first question that the Daily Mail asks is this aliens? And so far the answer has been no, and everyone's been super disappointed. But one day it will be, and it will be great.
Yeah, and of course, aliens, life, maybe we're talking about alien plants, right? Because of course we will only see the elements, so we could see a lot of oxygen, methane, and so on. So there's there are specialist bio exoplanet scientists, right? They model what could be real signature of presence of life, but could be we don't necessarily knew whether there will be intelligence or. But then we could look for your megastructure, of course.
It's a shame that if we do discover anything like this, it's likely to be billions and billions of light years away. And unless they're far better at self-preservation than we are, they might be extinct by now. Civilization could have risen and fallen. So we could find a universe absolutely teeming with intelligent life billions of years ago, and now we're just super late to the party.
Well, in these exoplanets we're looking at are 100 light years away, or we will look at even much closer planets. I mean, this is all in our galaxy, and it's all in our neighborhood because these are weak signal. We stay nearby. So in that respect, we could be just seeing their old television program.
Well, it's got to be better than ours. So, hopefully they're going through some kind of golden age of television.
Yeah, I'll flick through all the channels that we've got on TV here and be like, nah, I'm not feeling any of these. I'll switch to the Alien channel and watch. Yeah.
I've got every streaming service known to man, and there's still nothing to watch. So I need to start looking outside of the solar system.
Something that's unknown to man.
Exactly. We're incredibly excited to have Dr. Giardino joining us at DataFest this year. And you can hear much more about her work on the James Webb Space Telescope on the 3rd and 4th of November at the EICC in Edinburgh. Don't forget that listeners can use the code TLQPodcast, all caps, to receive an exclusive 20% off DataFest ticket prices. So go and get yours now at datafest.global.
And finally, on to the last question. Each episode, we pose our listeners a question and invite people from around the world to offer their thoughts. We'll read the most interesting ones out on a future episode. Our question this week is, what discovery that the James Webb Space Telescope could make would be the most significant for humanity?
And that's it from us today. We'll be back next time with more insight, innovation, and wild speculation. Feel free to drop us an email to say hello or to suggest a topic we should cover, make corrections if you like. You can reach us at datafest@thedatalab.com, or you can find us on Twitter @datafest_.
Thanks for listening. Join us again next time for another episode of The Last Question.